Hello, everyone. I'm Yuying. I'm the fourth-year PhD student from Indiana University. Today, I'm going to talk about the on-loss functions for deep learning-based T60 estimation. So first, let's go to the why T60 matters. The reverberation time, we call it T60, influences the amount of reverberation in a signal. Here's like 4 different spectrograms from King speech to when T60 increases. So the King speech is really clear here. When T60 increases, we can see it blurs for the high frequency magnitude step by step. And the T60 tells how long it takes a given signal to decay by 60 dB. And the high T60 times indicate more reverberation. And it contains meaningful information about the room environment, and it also discloses the information about the corresponding room impulse response. By estimating the T60, it helps with accuracy analysis and the reverberation. For the previous studies, they show different features like MFSCC, the Melford frequency step coefficient, and the Garber feature vectors, and short-term room mean square, the RMS. And they using the different model structures. The traditional one, the hidden Markov model, the HMM, the multi-layer perceptron, MLP, and the convolution neural networks, the CNN. And also for the previous studies, most of the models using the mean squared error instead of any explore other cost functions. And for the problem formulation, we have the objective to investigate the impact of the pure classification, the pure regression, and the combined classification regression-based loss functions for T60 estimation. And our method is to using the joint network with a composite classification and regression-based loss function for estimating the reverberation time. Here is the whole view of our network architecture. We have 3 different parts: the data pre-processing, the feature extraction, and the composite T60 estimation. For the first part, the data pre-processing, a reverberant signal can be modeled as a convolution of King speech, the signal ST with the room impulse response, the room impulse response HT. XT equals to convolution between ST and HT. That's the input out data pre-processing part. And then we compute the short time Fourier transform, the STFT of the reverberant signal, and then decompose this into the magnitude and the phase theta terms. And we concatenate the log magnitude, the sine theta, and the cosine theta a long time to form a combined feature vector, which is the concatenate input as our output for this part. And for the feature extraction part, it consists of 6 2D convolution layers with red look activation function, and the batch normalization is applied after each convolution layer. And the number of kernel filters is set as follows: the 16 kernel filters for the first 2 convolution layers, and 32 for the middle 2 layers, and 64 for the last 2 convolution layers. And the max pooling is performed after the first 2 convolution layers, the middle 2 convolution layers, and between the last 2 convolution layers. And its kernel size set to 2 by 2. And here's the most important part, is the composite T60 estimation. We have 2 related tasks performed with shared feature input. The pure regression is directly estimates the T60, and the classification part, it do the T60 classification and also the classification-based T60 estimation. And for the regression part architecture, it has 1 convolution layer with ReLU activation function, and also follow with the 2D average pooling layer. The kernel size set to 3 by 3, and the leaky ReLU activation applied, its negative slope is set to 0.1. And a fully connected layer with the ReLU activation applied as the output layer. And we have like a composite T60 estimation for the classification part. It's composed into 2 subtasks. The first is the classification directly. It predicts the probabilities of each T60. And its architecture has like 2 fully connected layers with leaky ReLU and softmax activation functions applied, and also batch normalization applied to both layers as well. And the classification-based regression part is we're using like the weighted sum between a vector of the reverberation times and the classification probability output computed this part. And the TI here denotes the T60 of the ith class, and H denotes the number of classes. Here we propose like 4 different cost functions and use it to train our network. So the first one is a combination of the cross entropy loss and the mean square error loss. The cross entropy loss is compute the classification based loss, and the mean square error is using for compute the regression part. And we use the beta as a weight control parameter. It's range from 0 to 1. And the second loss function, cost function, is incorporates the classification-based regression loss. And so we add another weight control parameter alpha here, and also it ranges from 0 to 1 to control the direct classification and the classification-based regression. The third cost function, we incorporate the evaluation scores of Pearson's correlation coefficient, the PCC, and the Spearman's rank correlation coefficient, the SRCC. So we take the second loss, the B cost function, and minus the absolute value for the PCC and the SRCC. And the last cost function, we incorporate the mean absolute value error from the regression task. So we can see like the mean the MAE we calculate for the pure regression and the classification regression task. So for the experiments, the data set here we're using is the teaming corpus. And we randomly select 5,500 and another 500 sentences to construct the training, validation, and testing data sets. And all 6,000 utterances downsample to 8 kHz. We simulate room impulse response from 11 different rooms with image method. And the distance between the receiver and the speaker is set to 1 meter in all cases. We also select the 13 different reverberation times, ranges from 0.3 second to 1.5 second with steps of 0.1 second. 65,000 reverberant utterances for the training set, 6,500 reverberant utterances for the validation set, and another 6,500 reverberant utterances for the testing set. And due to the variance length for the room impulse response, all the room impulse response are 0 padded before the convolution to make the length of each room impulse response the same. And all clean signals cut to 6 seconds before the convolution. And all the model training with about 4 cost functions have like the same parameters. The baseline set to 50, optimizer set to Atom, and the learning rate set to 0.001. The iterations we set to 100 epochs, and all the experiments with the different combinations of alpha and beta to determine the best combination for the different approaches. So for the evaluation, we evaluate the performance of the proposed system compared with comparison approaches. And there's like a T60 estimation using the CNN from Brian 2020, and the T60 estimation based on spectral temporal modulation filtering from Sean 2013. And we using the MSE, MAE, PCC, and SRTC as our evaluation matrix. For the MSE and MAE scores, it means it greater than 0 with no upper bound, but the lower value indicates better performance. And the PCC and SRCC scores, it ranges from -1 to +1, and the higher value indicates better performance. And here is for the same room comparison for different approaches. For the MSE and MAE, the pure regression task the CNN has a better performance on pure regression task when seen room in testing set. And the classification-based regression task here, the cost function C when beta equals to 0.4 and alpha equals to 0.2 gives the best performance with classification-based regression task. For the PCC, cost function D when beta equals to 0.9, alpha equals to 0.1 gives the best performance across both the pure regression and the classification-based regression task. For the SRCC, cost function C when beta equals to 0.4, alpha equals to 0.2 performs best for classification-based regression task. And for the cost function D, when beta equals to 0.9 and alpha equals to 0.1 performs best for regression task. And for the unseen room comparison for this here, except for the pure regression task, all the other tasks, they have like a similar trend as in the same room comparisons here. So for the pure regression task, the cost function A when beta equals to 0 gives the best performance of pure regression task, and when unseen room here in testing set. So for the conclusion, we think our approach incorporates composite classification and a regression-based cost function for training a deep neural network that predicts T60. Our approach is different from recent method and benefits from the two tasks. Our approach benefits from dividing the classification tasks into two subtasks. The results show that the trade-off between the weighting classification versus the regression task does influence results. Thank you.